Effect of time shift in frequency domain can be seen from shifting a cosine. If we shift a cosine by 90 degrees, as we know the formula cos t minus 90 degree equals sine t, so we get a sine. To view it in the frequency domain, these two impulses, they represent a cosine. If we rotate them by 90 degree, which means shift the phase by 2 pi f t by 4, then for positive frequency this is a minus 2 pi f t by 4 clockwise rotation. For a negative frequency this becomes plus 2 pi f, and we get a sine. The fact that a time shift of t by 4 gives rise to a phase shift of 2 pi f t by 4 is a special case of a general relationship which says that n naught time shift gives rise to a phase shift that is 2 pi k over n naught. The derivation is in my book, but you would have seen this relationship in this form in many DSP texts. St with the Fourier transform SF, then St minus t naught, the Fourier transform of SF multiplied by e raised to power minus j2 pi f t naught. Now this is nothing but a complex sinusoid we saw earlier, with the only difference is that this is a frequency domain complex sinusoid because the variable is f. It has n q components, cos and sine, and it gets multiplied with the actual Fourier transform of the signal. The second way to look at this relationship is that n naught is a constant in frequency domain. So this relationship becomes linear in frequency, and we say that the phase is linear. So shift in one domain is multiplication by a complex sinusoid in the other domain. An example of this is, we say that our Wi-Fi modem works at 2.4 gigahertz. So in time domain, we have to multiply our signal with a complex sinusoid of carrier frequency 2.4 gigahertz, which shifts in frequency domain the spectrum from 0 to 2.4. This is exactly the same thing. Now an impulse has a Fourier transform which is all ones. If we shift by 1 this impulse, then you can see that either the phases are changing of the corresponding frequency domain representation, or we can say that this DFT is being multiplied with a frequency domain complex sinusoid. This is something very beautiful you can see here, and both of these are the same.
In this flow graph, we are going to cover the effect of time shift in frequency domain. This is one of the most important exercises in DSP applications, and I believe that if you understand the effect of time shift in frequency domain, you understand a much larger part of DSP as compared to any other concept. So let us start. The title is time shift effect and corresponding ID is here, and we have made a slider with that ID delay, which is a delay in time domain. Remember that these boxes all they can be filled with Python statements. The sample rate is 32 so that we can see the exact stem plots, and the NFFT is again 32. I have imported the value of pi and I have imported the numpy library, which we will use to generate a vector that contains a single one and 31 zeros so that we can simulate an impulse in time domain, an impulse signal in time domain. This is also we have done before in the frequency domain exploration. Now we start with the signal source first, not the vector source, and we will see why we are doing these exercises. So the waveform is a cosine. I've chosen real values with a frequency of 1. So the discrete frequency would be 1 out of 32. One cycle in 32 samples. No offset, no phase initially. It's not really necessary to choose the throttle as the exact sample rate. You see my sample rate is 32, but the throttle sample rate is 32,000 because this is actually just the sample rate on which the flow graph is throttled. So if I had chosen it equal to 32, then the samples would have moved so slowly. This delay is governed by the slider. That's why the ID delay is used here. Then I want to see the output in time domain. After that, I will change this to complex so that I can take an FFT and I'm using my own QFFT blog as I've shown you before. This we can see here. It was just a simple FFT preceded by a stream to vector and succeeded by a vector to stream, just to make the flow graphs a little tidied up. Now, this is the confusing part, but if you followed me along until this time, you know that I'm using a time sink to show the spectrum. This is because I want to show those discrete spectral points, and that's why I chose the NF50 as just 32. When we have mastered this concept, obviously what we will do is that we will replace all these spectra through the QFFT GUI frequency sink. Now coming back, let us run the flow graph first and see what it does so that we can go ahead and delve into the understanding. So the waveform first and spectrum later. The waveform just contains of in-phase component. You can see this is a cosine. This is because our signal source was a cosine real, and the initial phase was 0, which you can see starting from the top sample. What happens when we give a delay of one sample? So let us focus on this first, and we will see that the top sample has moved to the right. This is what we have covered in the definition of a sample delay. Here, interestingly, now we have both I and Q components. This corresponds to the concept we explained in the lecture that a shift in time domain induces a rotation in frequency domain, a rotation by a complex sinusoid. How that happens, we will just see now. For a delay of 2, the I component goes a little smaller, the Q component becomes a little bigger. For a delay of 4, you already see that some kind of pattern is emerging. And if you have guessed it right, then after a delay of 8 samples, in time domain, we have a sine waveform, not a cosine waveform. And we already know that a cosine delayed by a quarter of a period becomes a sine wave. Why quarter of a period here? Because you see the NFFT is 32. So 32 divided by 4 is 8, and that's what we can see here, 8 samples. If you recall the definition of frequency, we can see that a sinusoid in frequency domain are two spectral impulses, plus 1 Hz, minus 1 Hz, the frequency bins, and with the amplitude of plus NFFT over 2, which is 16 here, at the bin minus 1, and minus NFFT over 2 at the bin plus 1. Plus or minus 1 because we have chosen the frequency as 1. If we chose the frequency as 2, the amplitude would have not changed, but the bins would have appeared at plus 2 and minus 2. If we keep doing this procedure, we keep delaying, then the I component appears again, and the structure is appearing again. And now this it becomes a sort of a cosine again. We will find out. And here we see two spectral impulses, both at minus NFFT over 2 equals 16. So why that happens? To find that out, let us go back to our vector source. We will disable the signal source and we enable the vector source, which I told you that is producing a vector of 31 zeros preceded by a single 1. So basically we are simulating an impulse in time domain. Let us enable this through E or selecting the enable option here. And now when we run the flow graph, now we can see that there is some problem of scaling. The amplitudes are very small, so we adjust our spectral resolution minus 1.25 to 1.25 so that we can clearly see what's going on. Here we are. The waveform is an impulse. We have a single sample with the value of 1 at time 0 and the rest are all zeros. As I said before, please do not get confused with this time here. We are using a time sink to show spectrum in this discrete form. Let us delay this signal by one sample. And this is the interesting part. A delay of one sample implies that the unit impulse, which was at time 0, is now appearing at time 1. What has happened in the spectrum is that the spectrum is not much different because a unit impulse is also a complex sinusoid with the frequency of 0. Time is 0, so the frequency here is 0. A 0 frequency implies that the value is 1 for the in-phase part and 0 for the quadrature part. Now, a delay of 1 implies that the complex sinusoid in frequency domain has an inverse period of 1. This is what we have discussed in the lecture, and this is what we have detailed in the text as well. You can see that it is completing one full cycle here. For a delay of 2, you will see that they will be completing 2 full cycles here. This is because the delay is 2. We have already discussed the relationship that a shift in time domain is multiplication of the spectrum by a complex sinusoid in frequency domain. This is what that complex sinusoid is. Let us go back to a delay of 1 so that we can see where do these values come from. So remember, this is not a time domain signal, this is a spectrum. So this is my bin 0, this is my bin 1. Let us zoom in on bin 1 and see what the value here should be. When we focus on this bin number 1, we want to find out how the values of the sine and cosine appeared. For this purpose, I just take you to my website and you can see that time shift. Right now we don't discuss mod n, but this is always implied. We are talking within a circular region of NFFT samples. So Sn minus n naught is minus 2 pi k over n naught. In this case, capital N is the NFFT. In our case, 32. Bin number is 1, so k equals 1. The delay is minus 1 because it's a delay, so it's minus 1. So minus 2 pi 1 over 32 into 1. Or if you want, you can say 2 pi 1 over 32 into minus 1. But in each case, the value of sine argument can be found as 2 pi 1 over 32 into minus 1, and if you take the sine of that, you will see that it will be minus 0.19 something. So that's how these values appeared, and similar goes for cosine. Delay of 2 would give a complex sinusoid in frequency domain with double the frequency. And remember, this will not be always be like that. The actual point is that the underlying signal is an impulse. So this is a constant in frequency domain. I chose this deliberately to show you the complex sinusoid that appears after a simple delay. If the signal would have been different and I have chosen a delay of 1, then the resultant spectrum would have been the spectrum of the actual signal, whatever it was, multiplied by a complex sinusoid of frequency of inverse period 1 in frequency domain. So we can keep doing like that, and we can see that all these signals have correspondence in time domain as well. Now let us go back to our signal source and see why we had two spectral impulses at frequency plus minus 1, but those impulses were all negative for a delay of 16. This is where we left. Going back to the argument, the frequency of the signal source is 1, which implies that the spectral bins are plus 1 and minus 1. So their values can be found by 2 pi k over capital N. Capital N is 32. So 2 pi 1 over 32 multiplied by minus 16. So this comes out to be minus pi. What's the value of cos plus pi? Minus 1. Cos minus pi, minus 1. Hence we see two spectral impulses here because the original signal had two spectral impulses which are just simply multiplied by minus 1. And the reason we are seeing only the spectral impulses in these two bins is that the actual signal, as discussed before, has the spectral energy only in those bins, and multiplication with all the rest 0 bins turns that complex sinusoid in frequency domain to 0, and only these two values are multiplied. I just thought that some of you might be thinking the following question. When we ran this flow graph for the vector source and the delay was 16, then why are there such a nice structure appearing in frequency domain? So starting from the original signal, an impulse at time 0, a constant spectrum. That means that a delay of 16 implies that the constant spectrum is multiplied by a complex sinusoid in frequency domain with an inverse period of 16. Let us see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So the period is verified. Why are these values plus 1 and minus 1? Because 2 pi into k over 32, where k is all the bins numbers, k over 32 multiplied by the delay of 16. If you will say it minus 16, but you can take that sign by default. 2 pi k over 32 into 16 implies that it is k pi. Sine k pi is all zeros. Cos k pi is plus 1 for even k and minus 1 for odd k's. So this is the reason we see a spectral representation like this one.
Finally, a digital signal is something which is sampled on both time axis and amplitude axis. Remember previously the discrete time signal was something which we were sampling on time axis only. So a digital signal is the one where the amplitudes are also quantized.